All right, folks. In this video, we're going to continue our discussion on special matrices. We talked about bandwidth last time, which is the maximum distance of non-zero elements from the diagonal. If I have a non-zero element here or there, you find a distance from the non-zero elements to the diagonal, either this or that, and you find the maximum that gives you the bandwidth. You have to do that, by the way, for all non-zero elements. So here's a quick example. If we have n by n diagonal matrix with no zeros on the diagonal, okay, then the density of that matrix is going to be 1 over n because we have only n non-zero values on the diagonal. Total number of elements is n squared, so n divided by n squared gives you 1 over n. So that's the density. 1 minus density is going to be sparsity. So the sparsity of a diagonal matrix with all non-zero elements on the diagonal is going to be 1 minus 1 over n. How's the bandwidth? Well, bandwidth is the maximum distance of non-zero elements from the diagonal, but because all of the elements are 0, except the diagonal elements, the distance, or the maximum distance, of non-zero elements from the diagonal will be 0, because all the non-zero elements are on the diagonal. So the bandwidth is going to be 0. However, if in the n by n matrix, okay, I have, or in other words, if all of the elements in the n by n matrix is non-zero, then the density of that matrix is 1, because the number of non-zeros is just n squared, is the total number of elements in the matrix, divided by the total elements in the matrix is again n squared, so you get the density of 1, and then the sparsity is going to be 1 minus 1, which is 0. So sparsity is 0. And what is the bandwidth? So bandwidth is the maximum distance of the non-zero elements on the diagonal. If the matrix is full and every element is non-zero, then the maximum distance of elements from the diagonal is exactly equal to n minus 1. And that corresponds to the distance of the element on the first row and last column. So if you assume there's one element here, the distance of that element from the diagonal is going to be n minus 1 entry, or n minus 1 elements. And as such, the sparsity is going to be, or the bandwidth is going to be n minus 1. Okay? All right, so in MATLAB there are functions, you can create a sparse matrix. The good thing about a sparse matrix is if you have a lot of zeros, you don't have to save the zero, and that makes the computation faster with MATLAB. So if you know that your matrix is a sparse, you can, or let's say you have a matrix and a lot of zeros in there, and you want to say, hey, just do not save all the zeros, just record all the non-zero elements. The function to do that is sparse. Say sparse A converts it to a sparse matrix S. Conversely, if you have a sparse matrix and you want to convert it to A and show it, then you use full. So this full function converts a sparse matrix to a normal matrix with all the zeros on the elements where they are 0. Okay? All right, so let's look at this example. I have an example. In this example, the matrix, the coefficient matrix, is this matrix, is a 3-diagonal matrix. That means it only has super diagonal as C's, diagonal as B's, and subdiagonal as A's. Okay, so this is A, the coefficient matrix, times x vector equals d vector. Okay, so we're going to look at how we can construct this matrix by some commands in MATLAB. So I'm going to lump all of my A values or A variables into a vector called A. Okay, so this A has A1, A2, A3, all the way to NA, n minus 1. Similarly, I can have a vector B, which has only the elements on the diagonals, B from B1 to Bn, and similarly for super diagonal C from C1 to Cn minus 1. All right. And on the right-hand side, we're going to have a vector for that. This is d1 to dn. Okay. So given that I have these 4 vectors, I'm going to construct this matrix in like one line command. So we're going to say the matrix T, which is this coefficient matrix, is equal to a diagonal matrix whose subdiagonal is A. So by -1, MATLAB understands that this is a subdiagonal. So it puts the whole vector A in the subdiagonal. I'm going to create another matrix with diagonal to be B. So the index is 0, means all the elements go to the diagonal. And then the last term is diagonal C, which means all the elements in the C vector go to super diagonal. So this is going to be super diagonal, diagonal, subdiagonal. You add them up, you get the total matrix with 3 diagonals. You can go ahead and use backslash operator to solve for the solution. It's just T backslash D. Okay. So this was a function to create a diagonal matrix. Now there's also a function to create sparse matrix. Okay, so we're going to do the same thing using now another function. It's called spdiags. So we're going to put A, B, C on subdiagonal, diagonal, and super diagonal. And the dimension of the overall matrix is going to be n. So we're going to have an n by n matrix. All of them are 0, but subdiagonal is A, super diagonal is C, and diagonal is B. So these directives refer to where the vectors are going to sit. Okay, so after we have S, then we can do S backslash D. So we're going to solve the system. So you see now, this time I create my matrix with just one function. Here was like basically 3 functions, I add them up. Okay, so the next section of this chapter is on pictorial representation of EL conditioning. So last time we saw that the matrix was sensitive to perturbation, and we call it basically that matrix or that matrix has a large condition number. So pictorial here, I'm showing how we can say a matrix is EL conditioned with large condition number. So imagine in 2 dimensions we have 2 lines crossing at one point, and if I perturb, let's say, this line or that line, so this line is going to have different intercepts. It's going to move up and down a little bit. So here's the range that this line can change. So meaning that if you perturb the coefficients in the A matrix, we are basically changing one of the lines. We can also change or perturb the other columns of A. So that means we're changing the slope or intercept of the other line. So anyways, by doing the perturbation, we're going to have a range for this line and range for that line. So at the end of the day, the uncertainty in X will be the 2 end points of this diamond or parallelogram, right? So we say, okay, the uncertain x1 is, between this and that. And this is where the perturbation actually crosses. Similarly, if you go to the case where the matrix is EL conditioned, which means the slope of these lines are very close. I mean, it's pretty much like we have one line, but a little bit of variation in either the slope or the intercept. So as such, we get these 2 lines which have very similar or close slopes. So now if I perturb them, move them left, right, or up, down, and find this diamond, which is the range, the intersection of the 2 lines can move. So the range of the x1 in that case would be the difference between the 2 endpoints of this diamond. And you see that this distance, which is the major diagonal of this parallelogram or the diamond, this major axis is bigger than this major axis. So it means uncertain x1 is bigger than uncertain x1 in this case. So this is ill condition, this is well condition. Okay, and so we can basically see this behavior by looking at the elements of a matrix. If the elements of a matrix are so different, like in this case, I have 10 minus 6 in here, and then on some line I have 10 to the, or 1 or 15 times 10 to the 3. So overall, the difference or the range between the elements is something in the range of 10 to the 9 maybe. If you assume that this is in the order of 10 to the minus 5, this is 10 to the 4, the difference is about 10 to the 9 or maybe 9 orders of magnitude difference. So in that case, this matrix is very close to be ill condition with large condition number, because the difference between the numbers or the difference between entries in the A matrix is rather large. So one way to fix the ill conditioning problem is, if something is very close to 0, just set them exactly equal to 0. So we're going to go ahead and set these equal to 0. In that case, well, for this matrix, we can easily see that the matrix is ill posed or ill conditioned, because once we put all the small elements to 0, we get a row with all zeros. So that clearly shows us why the matrix is not well behaved. Okay, so approximating small numbers by like 0 would definitely help and gives us a vision whether the matrix is singular or not, or whether the matrix is ill conditioned or not. Okay. All right, so the last section of this chapter is singular value decomposition. This technique is used when we want to deal with the linear system. So we talked about this linear system before. Linear system can have, indefinite number of solutions, no solutions, or unique solutions. The question is how we can really find how many solutions we have is by just looking at SVD, or singular value decomposition. So SVD decompose a matrix to 3 matrices, U, W, and V. U and V are rectangular matrices, and W is a square matrix. W is a diagonal matrix. It has only non-zero elements along the diagonal. The other 2 matrices are full. Okay? So by definition, U and V, which are rectangular matrices, are orthogonal, which means U transpose U is equal to identity, and V transpose times V is also equal to identity. Okay? So for SVD, we don't really need A to be square matrix. Even if A is rectangular, we can do SVD. Okay, so SVD is different from LU. So LU factorization converts a matrix to lower and upper triangular matrices with some P permutation matrix. Okay, and so LU factorization is very much known in the community, and it's used for solving linear system. If you have a linear system, you do LU factorization, and then you start by just looking at U times the unknown, and then L times Y, something like that, and you solve for the unknowns using back substitution. Okay, so this is pretty much like Gauss elimination. Gauss elimination, basically we follow LU factorization. However, this one is singular value decomposition. It's different from LU factorization. Okay, so in SVD, after we decompose the matrix A to U, W, and V, okay, so we talked about U and V that are orthogonal, and then W is diagonal. So this W actually helps us see whether the matrix or the system is solvable, whether we have a unique solution or indefinite number of solutions or no solutions. In the next video, I'll be discussing how we can basically estimate whether the system has infinite or no or unique solutions by just looking at this W, which is the diagonal matrix. So stay tuned, and thanks for watching.